Good morning, everybody. It's 10 o'clock, so why don't we get started. Thank you for joining today's C3 Climate Change presentation. My name is David Pott. I'm the Climate Change Coordinator for the U.S. Fish and Wildlife Service's Pacific Region based in Portland, Oregon. And I'll be emceeing today's webinar on behalf of C3, the Pacific Northwest Climate Change Collaboration, which is a federal interagency group. Let me now introduce our speaker, Charlie Luce, who will provide us a presentation on precipitation declines in the Pacific Northwest. We've seen lots of research interest on declining snowpack linked to increased temperature due to climate change. But this is an interesting new twist, and to what extent is a long-term decline in precipitation playing a role? This is a timely topic for sure. I just received an email from a colleague on Friday who sent me some data from Timberline Lodge at Mount Hood indicating the lowest snow recording at that station ever recorded for late January. Our speaker, Charlie Luce, is a research hydrologist with the U.S. Forest Service at the Boise Aquatic Sciences Lab. He's authored numerous papers and reports on hydrology, watershed processes, sediment and erosion, and climate change. And in the announcement email that we sent out to you all, we featured a recent publication on today's topic. So Charlie, welcome, and thank you in advance for your time today, and take it away.
Great. Thanks much, Dave. First off, just want to acknowledge my co-authors in this effort, John Abasoglu at University of Idaho in Moscow, climatologist there, and Zach Holden from Missoula with Region 1 in Missoula, fire ecologist there. And we've been seeing some changes due to climate change across some of our valued resources in the Pacific Northwest. Many of our mountain forests have been declining due to insects, fires. We've seen changes in our water supply and certainly effects on our fish populations. The common thread running through all of those is an issue with water, and changes in stream flows have been identified in the past. There are several papers fairly recently describing some of the declining Pacific Northwest stream flows, some in specific states, Idaho, Washington, and others more broadly across the region, the Upper Columbia. One thing to note about some of these trends is that they're exhibiting two kinds of non-stationarity, which is two kinds of trends. One is a shift in the mean behavior, and another is a change in the variability. And particularly, when we look at one of these, and we look at the driest years, we're seeing some actually pretty large changes over the last 60 years. And this is the Luce and Holden paper from 2009. And we're seeing some changes on to the order of the 30 and 40% declines over the course of 60 years. So what that looks like when you plot it out in time, so across the bottom axis here is years, and the annual flow, in this case for the Boise River here in millimeters. And we see that the wettest years in this basin aren't changing much. The mean and median, shown here in red and the solid black line, are changing a little bit, but the strongest declines are really in the driest years. And when you take a look at that for all the stations across the Pacific Northwest where it's reasonable to look at that, stations that haven't had a lot of upstream impact, it's starkly visible how the driest years are showing the strongest declines. The wettest years, on average over the region, are hardly showing any declines, although it is mildly there. And then in median and mean years, some change as well. So an important question is why. There are two potential causes for a decrease in Q, and with hydrology we just have the simple mass balance that flow is equal to precipitation minus evaporation. So the two possible reasons that we could have for the change are evaporations increasing or precipitation decreasing. It's an easy enough set of hypotheses to test. One way to test that is to take a look at the HCN2. So the HCN are our longest term, what are called co-op stations, where people have measured this over the course of this period of time. And those are the ones that are being used as sort of climate indices for testing things like global change GCMs, general circulation models. And if we look at the HCN2 trends in the precipitation gauges, looking at the percent change here in the 25th percentile, the changes aren't all that great in comparison. In fact, even though there are a few statistically significant red dots in here, if you look at what's called the field significance, i.e. the fact that you're really testing a whole bunch of stations, there's some probability that some will randomly come up statistically significant anyway. This field of stations is not statistically significant. There isn't really a noticeable decline. If you actually took the value of the average decline over that, it's about a 6% decline, which certainly doesn't match what we've seen in the streamflows. Well, that seems easy enough, but then we have to think about the evaporation question. And what's nice is, again, there's a pretty good, pretty simple control on evaporation. So the incoming energy from the sun and from the atmosphere in terms of radiation is here. That's net radiation. And that has to break out for a given surface, can break out into evaporation or change in temperature. So fairly simple. There's not a lot to go beyond that. These are fluxes that either go into the atmosphere or into the ground. And then these are what are called latent heat fluxes. So you can have one or the other based on a change in net radiation. Now we know that there's been an increase in net radiation. That's what global climate change, the greenhouse effect, is all about. It's increasing CO2 in the atmosphere, which has a stronger emissivity, so we have more downwelling long-wave radiation. The amount we have is about 1.8 watts per meter square so far, and that's for the AR4 report that was released a few years ago. That's about equivalent to a Christmas tree light bulb on every square meter. Doesn't seem like a lot, but certainly adds up over the course of 24 hours a day and course of a year. And we can evaporate a bit more water with that. And that's what this dashed line is. If you take that equivalent energy over the course of time, here's how much more water you can evaporate. We also thought, but if you look at how much water has been lost from all the basins, so here they are arrayed on the bottom axis according to how much runoff each basin has, and this is how much each basin has lost on the left axis, and that equivalent given in watts per square meter on the right axis. We see that 1.8 watts per meter squared doesn't really help us much explain the large amount of loss that has happened in these streams. Now, if we add to that the fact that the snowpack melts a bit earlier, so we just started searching for could there be any additional radiation coming in. So the snowpack melting earlier allows the sun to shine on ground and forest instead of on snow. Snow reflects a lot of light, so we have an increased net radiation just from that effect as well. But still, we're not seeing a lot of, certainly not enough to explain the trends. So we had two hypotheses, and we've pretty well rejected both of them, which isn't a good place to start things. But when we go and plot where the precipitation stations are from that first test, as compared to where the basins are, an interesting pattern emerges, and that's that none of the precipitation stations, or almost none, altogether about 13 of them, but broadly speaking, and I'll show that on the next slide as well, none of the stations that measure precipitation are in the same places that we're measuring streamflow from. So we look at these basins that are relatively undisturbed, and they're mostly mountain basins. The precipitation gauges are located where people have lived for a long time. They're part of a volunteer network where volunteers go out and take measurements every day at set specific times and have, in some cases, for more than 100 years. But therefore, those are in places where people live, which tend not to be in the highest mountain elevations. And although there are some stations up there, they tend to have more broken records. What's interesting is when you plot the highest elevations of the watersheds, their average elevate in red there, the average elevations in blue, and the lowest elevations in green, and compare those to where the precipitation gauges are arrayed across the region. So I have the longitude here going from west to east, and then the elevation here, because there is a slight trend as you go across the region. But you can see that the pattern in where the precipitation gauges are is about the same place that the lowest parts of the basins are, i.e. the precipitation stations are in the valleys, and the same at essentially the edges of the watershed. So we're really not seeing from those precipitation gauges what's going on inside the watersheds, which are higher mountains. A phenomenon called orographic precipitation explains in general why we have more precipitation in the mountains than we have at lower elevations. And that's when you have winds blowing off of the ocean up over the mountains, in many cases where we live, running north-south, and forces the air up over the mountains. It forces cooling of that air, which then condenses into clouds and causes precipitation. So our new hypothesis here is that changes in the orographic precipitation might be explaining the changes in stream flow. And there's some reasonable basis for that. When we look here, this shows that if you look at El Nino, that there's an effect on how the precipitation is distributed in the region. So some of the interior lower valleys here, although this is relatively higher than this, but just in general, we have a mountain range here and a big mountain range here and one sticking in this region. But in general, what we're talking about here is that those mountains are more sensitive to El Nino than the lower elevation places. So if we look in places like the Willamette Valley, the valleys between the mountains, we really see that the precipitation decreases with ENSO at high elevations and actually have an increase in precipitation in some of these central locations. And that's been shown by others before, that there's this sensitivity to El Nino, and so you have interannual variability. When we go to the physics of understanding that, we can actually see that there's a precipitation correlation with regional westerly wind speeds. So if we take a box from 47.5 north to 42.5 north, extending out of the ocean a little ways to 130 west, and then out here to about 115 west, which is in this neighborhood, you just take the average November through March wind speed. That's how that correlates to the average November through March precipitation at each of these stations. The squares are snowtail stations. Those are generally at higher elevations. And the round ones are our HCN stations that we did the test on before. And we note that many of the HCN stations are not correlated to wind, whereas a lot of the snowtail stations, which are up in the mountains, are. Unfortunately, we can't take a trend off the snowtail stations because they've only been around since the 80s. And that's kind of a short time period to try and get a trend explaining things, and certainly doesn't relate to the 60-year long trend that we saw in the stream flows. We can also take these three strips here with these three strips with slightly lighter white backgrounds here and view them in profile. So here's just the average elevation of those three strips, showing again the snowtail stations at higher elevations and the HCN stations at relatively lower elevations across the region. And gives you the same general picture that the higher elevation ones, particularly at where the mountains are north-south running, show a stronger correlation to the wind. Now, along with that change is the fact that the wind, that average wind speed across the northwest, is showing a very similar pattern to the stream flows. A little bit of decline in the 75th percentile mean, but a much stronger decline in the slowest flowing years. In this case, these are also the driest years. So that ties things up pretty well in a nice, neat picture for that 60-year period. But we really need to think more broadly about how does this tie into our larger, the bigger scheme of things, the longer term. So certainly we have the climate cycles like El Nino and Pacific Decadal Oscillation, the Pacific North American pattern, and we have global change going on, long-term changes going on behind all this as well. So how do these things fit in to that 50-year pattern, or 60-year pattern in this case? So if we take a look at the Boise River, that's been gauged since 1912, and we can take a look at the 25th percentile in stream flow, again shown here with a spline to that quantile fit here. But along with that, we can show a smoothed PDO, which takes out the interannual up and down bounce in the PDO, but just shows this nice smooth pattern. And there's quite a bit of similarity there, so worth knowing about and good context. And we do see a good, strong dry period here in the 30s, and we're showing fairly similar amounts of runoff now. And certainly that ties to the precip. If we dig back even further in time, taking a look at some work that's been done with tree rings, I have little blue circles here in both of these tree ring reconstructions for the 1930s, which, as we know, ties in pretty well with what we're seeing now. And if we look back through time, the 1930s are relatively a dry period. So certainly a question to ask is whether we expect the trend that we've seen now to just bounce back up as it has in the past year, or to stay down, and whether it's just tied to climate cycles that have always existed, or if there's some other climate change contribution to the process. When we take a look at the effects of these various climate modes on the wind speeds, so we have U700 here, which is the westerly wind speed at 700 hectopascals, as a function of El Nino, the Pacific North American pattern, and PDO, we get these black points. And if we take a look at the trend in the modeled wind speeds, the slope of the mean is about 1/2, and the slope in the extreme here in the slowest years, the slope is about 1/3 of the actually observed trend. And what that means to us is that these changes that we've seen in recent history are a combination of these changes in these climate cycles over that period of time, but also some other effects. Now, if we look at expectations of what we've seen over these 60 years compared to what we might expect in the future, we see that the mean of the various CMIP5 models here compared to the current mean isn't much different. And here's the mean for this last 60-year period in blue on this axis. So we see a decline relative to that 60-year mean in these among these 24 models. So their average is about 10% lower. And what that means is for the future, the average might be looking like conditions do now, which in some relative sense are lower than the average seen over the last 60 years. So what's driving that, and why do we expect that to tie into climate change? One of the things is this equator pole gradient, also called the meridional temperature gradient, and that's the difference in temperature between the poles and the equator. And that difference is declining. So if we take a look at this axis here, we see that it's in negative terms here, so the upward climb here is actually showing a declining gradient between the poles and the equator. And you've probably been hearing a bit about that on the news of late with the discussion over the polar vortex discussion for the cold temperatures back east, being partly driven by this change in gradients. Likewise, the contrast in temperature between ocean and land, particularly in the winter, so the land is usually colder in the winter, but as we add CO2, the land is expected to warm faster than the oceans. And so again, the gradient is declining if we take a look at the sense of this axis again. And what that means when we take a look at a map like this, here's our region with the black circle here. The red area here shows that this area has been warming and the atmosphere getting thicker here faster than what we're seeing down further south. So what we see here, just in this particular region, is a decline in the gradient north to south. And actually, there's also one here, which is a good example that I'll bring up later, because they've been seeing the same things in northern Chile as we're seeing here, i.e. a decline in the mountains while the lower elevation gauges are not showing much change. Now, any place that you look on this map and you see, in the closer to the equator, places aren't changing much temperature, whereas further north they're warming, those are places where gradients are decreasing. If you see places that show they're getting colder, closer to the poles, like across here, those are places where the gradients have been increasing. I'll be showing another map like this again, but this is the historical trends in that pressure map. And what that translates to in terms of interannual variability, if we take a look at the atmospheric thickness up here in the northern region compared to the southern region, mostly over ocean, and the northern regions mostly over land in British Columbia, and compare that contrast in temperatures or pressures to the winds. So the wind's on this axis, the delta H is on this axis. We see quite a strong correlation between the two. So the years with strong winds are the years with a very strong difference in pressure. So if we look in the future here, so now we're looking at 2070 to 2099 versus this period 1950 to 2005. We look down here, and the changes further south of us are small relative to the warming further north of us. So that's what has been explained as one of the signatures of climate change, is that northern regions warm faster than more southerly regions. And certainly we're seeing that with us relative to the eastern Pacific in this region. And when we look at the different models, I want to back up. So when we take a look at what that means for future wind changes, what that predicts is on a line running through this region, we're seeing fairly substantial declines in wind speeds on the order of about 1 meter per second, which is nominally about 10%. And when we look across models, again, at the differences between these regions, so here's the average. Each one of these dots represents one model. So the models that are showing the biggest declines are the ones that are showing the biggest warming in the north compared to what's going on in the south. So an important question is missing the effect of mountains on precipitation important? Is that an important question? Because we've certainly been hearing about other declines. And the important aspect of this is how it affects our adaptation choices. So we've been hearing about declines in the April 1 snowpack. Certainly here's the historical picture. An important thing to note here is that we're seeing strong declines in both the coastal mountains, the Cascades, as well as the northern Rockies. And similarly, we've heard about changes in streamflow timing. This has been indicated as one of the biggest effects we have in Western hydrology. And again, the effects are nearly equally strong near the coast as they are here in the Rockies. Now, contrast that with what we understand about the physics and the sensitivity. This is a really nice, clear, simple picture given by Ann Nolan and Chris Daly, looking at the most sensitive snow being places in the Olympics and Cascades, and relatively less sensitive out here further to the east. Similarly, Phil Mote put together a very nice paper in 2005 and a related one in 2006 that describes relative sensitivity. Again, so if you take a look at these arrows, a straight downward pointing arrow would indicate very strong temperature sensitivity. A straight east pointing arrow indicates strong precipitation sensitivity. And if you look here in the Cascade range, you see more strongly downward pointing arrows. And when you look here in the northern Rockies, quite a few nearly east pointing arrows. Very strong difference in sensitivity across the two, but nonetheless very similar outcomes, i.e. both are showing declines in snowpack. And here's another one based on so this is a third line of inference showing very strong differences in sensitivity. This is based on spatial patterns, and here we look in the Cascades and other parts of Oregon showing very strong sensitivity to temperature increases versus some, though lesser, sensitivity to temperature in the interior. So reconciling those two things is important, because when we apply those ideas to how we manage water resources in the future will be important. And one of the assumptions we've had in understanding past changes is that the precipitation has not been declining. We've combined that with maps from AR4 and now AR5 showing that precipitation is likely not changing much, or possibly even slightly increasing over the region from the GCMs. And our interpretation has been that the main effect we'll be seeing is the temperature effect on timing. And so here's an example of how Vic is showing changes in streamflow for the Boise River, which is part of our interior set. So we see now we have a very nice, strong snowmelt peak. And in the future, we might be seeing something more spread out with some midwinter flow events. When you difference those, when you take the difference between them, gives you more runoff in the winter period here and less runoff in the summer when it's needed for irrigation. So the fairly obvious engineering solution that sits there when you're presented with a graph like that is to build a dam or storage to collect this water on this side of this line and apply it here in the summer for irrigation. So you're replacing snowpack storage with dam storage. An important thing to take a look at is sort of this description of the seasonality seesaw, where we've had this long discussion of the center of timing. So you have runoff on each side, and they're balanced for the moment, and that defines your center of timing. If you move some of your runoff earlier in the year and you shift timing, you move it from this side of the seesaw to the other, you have to shift your center of timing. Now, similarly, you can start with that, but actually just lose some water, lose precip, so you lose summer runoff. Again, you'd still have to change the center of timing, and if you're just looking at the center of timing and not looking at the runoff volumes and the changes in that, you might interpret that center of timing as simply being a shift as opposed to a loss. You actually can't tell the difference just from that number alone. And in fact, an interesting way to look at the sensitivity of that, here's the Salmon River near Salmon, just an example from the interior side. The center of timing here on this axis versus the annual stream flow, you see a very strong signal there tied to total annual stream flow, which represents essentially how deep the snowpack was that you started with. And deeper snowpacks last longer is the story here, or as I jokingly say, tall snowmen take longer to melt than short snowmen. And the pattern here, the curved shape there has to do with solar angles, i.e. an extra inch of snow left around in April takes longer to melt than an extra inch of snow left around in June. But and there are certainly some ups and downs in here. Those are probably tied to temperature changes. The snowpack is sensitive to that. I don't want to suggest it's not. But the overarching, the big signal here is just the total amount of snowpack because it's a relatively cold region. Now, when you take that information together, you start to realize that what the future might look something more like what we've already seen in the Boise. Here's the observed flow changes, 1950s and 1990s. There's been a little bit of shift or advance in the hydrograph, so we see a little bit of an up here in March. But really, the big picture here is that despite very large declines in summer runoff, we're not seeing the winter runoff to make up for it. This also, a decline in precipitation also has consequences for vegetation, makes them more sensitive to insect attacks and other sources of mortality, including just direct death by drought and effects of fires. One of the questions that's been asked broadly is about the effects of climate change on fire, and here's one of the key ones there, the Westerling paper from 2006 describing all of these fires. The hypothesis there was temperature changing runoff timing, which changes fire extent. But certainly now we have some idea to understand why changes in precipitation leading to changes in annual runoff can also affect that fire extent, particularly in the sense that changes in annual runoff mechanistically affect runoff timing. So we can apply a statistical technique called path analysis, where we can take a look at these mechanisms and note that the flow of information, because there's a correlation between these two and it's a causal mechanism, that the flow of information from precipitation through annual runoff is about this Q number here. It's about 3 times greater than just strictly through temperature and back around. So if we're using temperature to give us our forecasts for future fire extent, we might be in error. It should be important to also bring in this precipitation side of it. So having a bit more information about what precipitation might do in the future is an important piece of the puzzle. Another way to look at this is to take a look at that temperature sensitivity map from earlier, and we note that the temperature sensitivity is much stronger at lower elevations than at high, whereas the precipitation sensitivity is stronger at higher elevations than at low. So you have a nice flipped signal there. And when you take a look, for instance, in the northern Rockies where the fires have been, many of the fires have been at higher elevations in this area, and these, I think Westerling said roughly 2/3 of the fires he analyzed were from this region. So the story there is that this high elevation precipitation sensitivity is what's driving the interannual variability in fire extent there. Fires are also important to fish, so particularly effects on stream temperature. A lot of you, I think, have seen the the work that Dan Isaac's done on stream temperatures, and here's showing some burned areas in the Boise River Basin and the relative increases in temperature across those. And one of the questions that's come up certainly with respect to fish and forests is, should we go in and treat forests, thin them out so that they look more like they did in earlier times? Often this involves people going in, either doing work by hand or with chainsaws or a number of other tools that we can do to help our forest adapt for the future, reduce the water stress, reduce the potential for fire spread. But certainly for fish, this also raises questions about management. Management has in the past had quite a strong effect on fish as well. So the balance between effects of fire on fish versus the effects of past management on fish is certainly an important question. And a group of us did some writing on this subject a couple of years ago. It's in this document describing some of the changes affected to forests and riparian areas and aquatic systems as a function of climate change, and how we might be able to best set up our adaptation to those changes. So I'd like to summarize here just the general story, and an important one is that there have been historical declines in runoff from Pacific Northwest mountains tied to declines in precipitation over the last 60 years. There's been a lot of sense that the precipitation hasn't changed in the past because we've relied on those HCN gauges to give us that information, but now we're realizing that those gauges are not giving us the complete picture. Knowledge of this trend is essential for understanding the snow and ecology changes over that period as well. So we've seen differential sensitivity. We've seen some places that have had a strong temperature effect and some with a strong temperature sensitivity, and places with a strong precipitation sensitivity contrast, but both give us declines in snowpack that are relatively equal. So temperature is a very big piece of some of the map, and precipitation's a big piece of another part of the map. And these insights from these trends may be informative for assessing what future changes in precipitation could be related to climate change in the mountains. I'll just finish here with a nice picture of snow in the mountains here on a nice Labor Day weekend in high elevation, which may change in the future. And here's the contact information, and as Dave mentioned earlier, here's the site where this presentation will be stored later. Thanks much.
Thanks, Charlie. Great job. That was a lot of information in 35 minutes there. So I just wanted to open this up to folks on the line. If first of all, if you could mute your phones on your end, I'm going to go ahead and unmute all the lines. So if you're not asking a question, if you could be careful to mute your phones or keep the volume down on your end, that would be great. And you can also send a question by chat if you prefer to do that, and I can read those off. So I'm going ahead here and unmuting all the lines. So if anyone has a question or a discussion point you'd like to raise, go ahead.
Charlie, this is Tim Mayer. I'll go ahead and ask a question. I just wondered, you showed the Boise River and the record there, and maybe it looked like there was some loss in the winter in terms of flow, if I got that right. And so, you know, it looked like it kind of supported your hypotheses there about declining precipitation. Have you done that for other streams too, some of the other watersheds that you looked at?
I'm not sure which slide you're referring to, but yes, all of the streams in the Pacific Northwest are showing declines. The declines are scattered through the year.
So I think you were comparing, the slide I was talking about, you were comparing the modeled, VIC model changes to the observed changes in the Boise River over the last 60 years, and you said, well, you know, we don't see the peak showing up in the winter like it's modeled to be. We see a decrease in winter and summer. So you've looked at other winter flows, and that pattern is common to the other watersheds too?
Yes.
Okay.
And
thanks.
it should be a little bit careful looking at this. There's a little bit of apples and oranges there, but it's showing the just the difference in patterns. It's not so much a decrease in winter flows in the observations. There is a little,
oh yeah,
but there's just not this big increase that's predicted
right.
by VIC.
Okay.
But again,
yeah, I see that.
Yeah, these VIC increases are tied to temperature changes that will be more strongly seen by the end of the century than have been seen now.
And Charlie, just a quick note, the VIC is the most commonly used hydrologic model in the region. Is that, do you want to say anything about that?
I suspect it is for climate change impacts at this stage. Certainly there are other models available, but this is one of the more, they were the RISA for quite a while, so I think that this is some of the most available information at the moment.
Okay, any other questions? I've
Yep.
got a few on the chat here. I could read one. One has to do with cloud seeding having an effect on atmospheric wind patterns. Is that something you would know about?
Not a lot. I know that conceptually cloud seeding is just supposed to help increase condensation of such vapor as is passing. Yes, that could conceptually, because when you condense moisture, you release heat, so it could conceptually change some fairly local circulation, but it shouldn't be broadly changing the wind patterns here.
Okay, and we have another question on chat. Why has the westerly flow declined over the past 50 years, but is not projected to decline in the future in the GCMs and the climate models? What is the physical mechanism for this? You've noticed that.
Yeah, let me find it. It is actually projected to change into the future as well. So the the pattern here is that, and what's driving the change in winds is that the northern box here has a trend of increasing pressure or temperature consistent with what global change is expected to do, and the southern box has changed very little. And if you look on an interannual basis, there's this strong relationship here that shows that what we expect to happen there. And this is the map of expected pressure changes in the future, which again show a strong, sorry, got to get on the right screen, strong change here north of us and a weaker change south of us. And notice that there's a reverse here, so there might be an increased subtropical jet while the subpolar jet is weakening. And so here's the CMIP5 projected winds, which are declining really quite strongly. And I think in these areas with plus signs, those are places that are showing 23 of 24 models agreeing in that decline. And then this shows that while a few of the models are showing on average increases in wind for this region, the great majority are showing declines, related again to this change in pressure differential.
Mm-hmm. And Karen, you have a question on chat, quite a long one. Would you prefer to read it or state it yourself, or do you want me to read it?
Yeah, I can just ask it.
Okay, great.
So toward the end of the slide presentation, you had that pathway chart showing temperature and precipitation and how it kind of flows into the ecosystem as a whole. And it seems like there might be a pathway missing, which is the pathway between how temperature affects precipitation patterns. So yeah, this is it. So we see directly that, we're talking about air temperature presumably here, and basically what this shows is that the temperature is relatively less important in a wet year than in a dry year, right? So precipitation has a higher effect on fire extent than temperature. And I think that's true, but I think it'd be interesting to see what this look like, or what the coefficient values are if you make the link between changes in air temperature and how that affects the precipitation patterns over the region. if that
Right.
would,
So
you know, increase it even more.
No. Well, let me. This brings up another good point. I don't know if that's what you necessarily intended. But yes, temperature, this is looking at the historical patterns. And over the history, there's not a lot of influence from temperature up to precipitation. But there is expected to be, with climate change and the broad warming of the atmosphere, warmer air holds per unit change in temperature more water. So as you lift one of those nice little atmospheric parcels of air that are always talked about in classes, a warmer parcel of air, when you squeeze it, is a more effective sponge for holding water and releasing it than colder areas. And so the reason that many of the GCMs project precipitation increases for the region is because of this, what's called the Clausius-Clapeyron relationship. The fact that warmer air holds more water and thus more can be squeezed out. So some of the question for the future will be, what's the competition between these wind effects and this Clausius-Clapeyron effect? And some of that will also depend on what how the ocean temperatures change relative to the land temperatures. So the control on the initial vapor pressure in that air parcel is the temperature over the ocean. So that's the one that we're really interested in relative to that Clausius-Clapeyron relationship. And if the temperature over the land increases even more, there might actually be, on the net, a drying effect, and we could actually see even further declines in orographic precipitation. So that balance between things is really something that can only be explored, say, in something like a regional climate model with more detail. And there are a lot of other effects tied to the slowing of winds as well. But there is sort of a positive nature of the relationship between temperature and precipitation expected in the context of a changing climate. And I don't know if that answers your question or if there's something more there that you're thinking that we can test with the historical data.
No, that pretty much gets to it. And then, you know, secondarily to that, the fact that part of the issue is how the precipitation falls. You know, whether it's snow or rain is also going to have a big impact. So, yeah,
right.
That was it. That was what I was looking at.
I'd like to just take that opportunity to repeat that none of what I've said in terms of decreasing precipitation, I mean, temperature is still a big effect on what snowpacks are doing. And we certainly see that in the Cascades a lot more strongly than we do in the interior mountains.
Charlie, this is Robes Parrish calling. I have another question on your Boise River PDO slide.
Okay.
It looks like that relationship is pretty clear with those two lines until you get to about 1990, when you show the PDO increasing back to neutral and the 25th percentile continuing to decline. And I'm just wondering if that's just a shortened data set or if that's actually like a decoupling of those two things or something else going on.
It's at the edge of the data, and I think especially with the a couple of wet years that we had, that this tail probably swings up again. Yeah, when you're getting over to the edge of the data and looking at this line, I wouldn't trust what these 5 years are doing there as part of a trend. My sense is that this actually flips up again, but I just didn't have the data for both sets at the time that I plotted this to capture that flipping back up. Although, a year like this, if it continues, could bring pressure back down on it. But yeah, they're certainly an open and interesting question that we won't probably be able to get a sense of for a few years yet.
Hey, Charlie, you touched briefly on management implications. So one signature in streamflow that's pretty common to clear-cut forestry is an initial increase in flows, and then as the plantations grow up and are consuming a lot of water, you get flows that are lower than what you would expect based on reference. Can you talk a little bit about management implications? You touched briefly in terms of fire resiliency and fire ecosystems, but what about managing plants fiber in relation to this decline in high elevation precipitation? precipitation?
The question was a little quiet, so I'm not sure if I'll answer the whole thing. Please feel free to re-ask if I don't quite get it. In terms of forest productivity and being able to produce carbon or fix carbon and produce fiber, in general, the expectation would be with less water, you're going to produce less wood, particularly in the drier portions of this range. Certainly there are some places where you could actually get a slightly opposite effect for particular species. But broadly, especially given what we've seen in terms of insects and mortality across the Northwest, my sense is that the increasing severity, because we're seeing most of the changes in the drought years, and increasing severity of drought is more challenging to the survival of these trees, we're probably seeing a pretty strong effect on how valuable these forests might be to how they fix carbon or produce fiber. Did that answer the question, or did I miss?
Partly. I'm also wondering in terms of silvicultural methods. I mean, we use a lot of clear-cut forestry, you know, and that kind of causes big peaks and dips in the hydrology. And also, you know, when you have plantations, they're consuming a lot of water and are very vulnerable to a drier period. So, right. You know, kind of, I'm wondering about more tree spacing or making uneven-aged management more common. As far as fiber production, are there implications from this in terms of, you know, can we continue on as we're going, or do we need to adjust, you know, silvicultural practices to deal with this?
Oh yeah, that's a good point, particularly in places where we're used to using more clear-cut forestry in contrast to shelter woods or thinning approaches where the older trees help shade and reduce the vapor transfer from the younger trees to the atmosphere. It could be that as we are losing precipitation, particularly in the driest years where we need to think about it, we should start adjusting silvicultural practices in wetter areas to look more like they would in what's already practiced in drier areas. Is that more directly helpful?
Yeah, absolutely. Thank you.
See, and Charlie, is a question on the chat from Paul. Paul's been working on a low-flow trend analysis in the state of Washington, and he's trying to differentiate between climate effect as opposed to human impacts, and he's just wants to make sure he's correct in interpreting that climate effects are strongly related to elevation. Is that something you recommend he look at?
That's what it looks like to us. Certainly the lower elevation stations haven't been showing, lower elevation precip stations have not been showing as much change over time as higher elevation. Mm-hmm. What's implied at higher elevations based on the stream flow changes.
Yeah, and I don't know, Paul, if you want to ask more about that, feel free.
Well, it's complex, but it is interesting because I think what you're suggesting is in basins that have high elevation, if we see a signal, that could be related to what you were finding with the precipitation changes and wind speeds. Of course, if you have like a lower elevation basin, you know, snowmelt's going to be big on a transition basin, and you know, the evapotranspiration might be a bigger effect on a rain-dominated basin. So, but it's very interesting. Thanks for sharing that, and it gives me food for thought.
Great. Yeah, I think one of the nice things it does is tie the complexity that we have in this region together. That certainly a broad range of hydrologic behaviors between the temperature sensitive, the places that are already rainfall dominated, and then the colder snowpack in the interior.
Yeah, the PDO graph I found particularly interesting, and I don't know what the end point of your graph is, but with the numbers I'm seeing, in the last 2 or 3 years, we've had very wet years, and so if you brought up the data to the most recent water year, that would tend to tip the tail back up, I'm pretty sure.
That's my guess as well. And when doing a spline like that, I don't put a lot of weight on what that tail's doing anyway.
Any further questions?
I just put something on the chat. I don't know if I'm...
Oh, go ahead. Yeah.
Are you able to hear me?
Yes.
Yeah.
Okay. Yeah, well, I mean, I could just repeat it. This is Bob Vadas in Washington State, but what I was asking was what can we expect for lake evaporation trends with atmospheric wind changes?
That's a good question. Not something that I have data on. We're looking at November through March winds in this case, and as well as temperature gradients in November through March. But McVicker and others, I think it's Troy. Anyways, T. McVicker has published a number of papers in recent years relative to changes in evaporation off of open water surfaces and others in summer months. Some of what he's described has been labeled global stilling, certainly a related phenomenon here, but I'd refer you back to those papers for summer ET changes.
Okay, thank you.
Great. Any other questions? Well, if not, Charlie, I want to thank you for today's presentation and the discussion that followed. Really appreciate it. Good job.